Valve operating mechanism. A cam gear is twice the camshaft lobe size of the crankshaft gear, and operates at 1/2 speed. Camshaft. Crankshaft. Figure 1-29, cam load on lifter body. Crankshaft gear, timing gear, figure 1-28. Cam drive mechanism opposed type aircraft engine. The function of the tappet assembly is to convert the rotational movement of the cam lobe into reciprocating motion, and to transmit this motion to the push rod, rocker arm, and then to the valve tip, opening the valve at the proper time. The purpose of the tappet spring is to take up the clearance between the rocker arm and the valve tip to reduce the shock load. When the valve is opened, a hole is drilled through the tappet to allow engine oil to flow to the hollow push rods to lubricate the rocker assemblies. Solid lifters/tappets. Solid lifters or cam followers generally require the valve clearance to be adjusted manually by adjusting a screw and lock nut. Valve clearance is needed to assure that the valve has enough clearance in the valve train to close completely. This adjustment or inspection was a continuous maintenance item until hydraulic lifters were used. Hydraulic valve tappets/lifters. Some aircraft engines incorporate hydraulic tappets that automatically keep the valve clearance at 0, eliminating the necessity for any valve clearance adjustment mechanism. A typical hydraulic tappet, zero-valve lifter, is shown in figure 1-30. When the engine valve is closed, the face of the tappet body, cam follower, is on the base circle or back of the cam. Oil hole, oil pressure chamber, oil supply chamber, cam, tappet body. Push rod socket, ball check valve. Cylinder. Push rod shroud tube, figure 1-30. Hydraulic valve tappets. Plunger spring plunger, 1-21. Figure 1-30. The light plunger spring lifts the hydraulic plunger, so that its outer end contacts the push rod socket, exerting a light pressure against it, thus eliminating any clearance in the valve linkage. As the plunger moves outward, the ball check valve moves off its seat. Oil from the supply chamber, which is directly connected with the engine lubrication system, flows in and fills the pressure chamber. As the camshaft rotates, the cam pushes the tappet body and the hydraulic lifter cylinder outward. This action forces the ball check valve onto its seat. Thus, the body of oil trapped in the pressure chamber acts as a cushion. During the interval, when the engine valve is off its seat, a predetermined leakage occurs between plunger and cylinder bore, which compensates for any expansion or contraction in the valve train. Immediately after the engine valve closes, the amount of oil required to fill the pressure chamber flows in from the supply chamber, preparing for another cycle of operation. Hydraulic valve lifters are normally adjusted at the time of overhaul. They are assembled dry, no lubrication. Clearance is checked, and adjustments are usually made by using push rods of different lengths. A minimum and maximum valve clearance is established. Any measurement between these extremes is acceptable, but approximately halfway between the extremes is desired. Hydraulic valve lifters require less maintenance, are better lubricated, and operate more quietly than the screw adjustment type. Push rod. The push rod, tubular in form, transmits the lifting force from the valve tappet to the rocker arm. A hardened steel ball is pressed over or into each end of the tube. One ball end fits into the socket of the rocker arm. In some instances, the balls are on the tappet and rocker arm, and the sockets are on the push rod. The tubular form is employed because of its lightness and strength. It permits the engine lubricating oil under pressure to pass through the hollow rod, and the drilled ball ends to lubricate the ball ends, rocker arm bearing, and valve stem guide. The push rod is enclosed in a tubular housing that extends from the crankcase to the cylinder head, referred to as push rod tubes. Rocker arms. The rocker arms transmit the lifting force from the cams to the valves. Figure 1-31. Rocker arm assemblies are supported by a plane, roller, or ball bearing, or a combination of these, which serves as a pivot. Generally, one end of the arm bears against the push rod, and the other bears on the valve stem. One end of the rocker arm is sometimes slotted to accommodate a steel roller. The opposite end is constructed with either a threaded split clamp and locking bolt or a tapped hole. The arm may have an adjusting screw for adjusting the clearance between the rocker arm and the valve stem tip. Figure 1-31. Rocker opposed engine arms. The screw can be adjusted to the specified clearance to make certain that the valve closes fully. Valve springs. Each valve is closed by 2 or 3 helical springs. If a single spring were used, it would vibrate or surge at certain speeds. To eliminate this difficulty, 2 or more springs, one inside the other, are installed on each valve. Each spring vibrates at a different engine speed, and rapid damping out of all spring surge vibrations during engine operation results. 2 or more springs also reduce danger of weakness and possible failure by breakage due to heat and metal fatigue. The springs are held in place by split locks installed in the recess of the valve spring upper retainer or washer, and engage a groove machined into the valve stem. The functions of the valve springs are to close the valve and to hold the valve securely on the valve seat. Bearings. A bearing is any surface which supports, or is supported by, another surface. A good bearing must be composed of material that is strong enough to withstand the pressure imposed on it and should permit the other surface to move with a minimum of friction and wear. The parts must be held in position within very close tolerances to provide efficient and quiet operation, and yet allow freedom of motion. To accomplish this, and at the same time reduce friction of moving parts, so that power loss is not excessive. Lubricated bearings of many types are used. Bearings are required to take radial loads, thrust loads, or a combination of the two. An example of a radial load would be a rotating shaft being held or contained in one position on a radial plane. Thrust load would be the rotating shaft being contained from moving axially along the shaft's axis. These radial and thrust loads are illustrated in Figure 1-32. There are two ways in which bearing surfaces move in relation to each other. One is by 1-22. Thrust loads. Straight roller bearing. Deep groove ball bearing controls both radial and thrust loads. No thrust loads. Rotating shaft radial loads only. Figure 1-32. Radial and thrust loads. The sliding movement of one metal against the other, sliding friction, and the second is for one surface to roll over the other, rolling friction. The three different types of bearings in general use are plane, roller, and ball. Figure 1-33, plane, roller, ball. Figure 1-33, bearings, plane bearings. Plane bearings are generally used for the crankshaft, cam ring, camshaft, connecting rods, and the accessory drive shaft bearings. Such bearings are usually subjected to radial loads only, although some have been designed to take thrust loads. Plane bearings are usually made of non-ferrous, having no iron, metals, such as silver, bronze, aluminum, and various alloys of copper, tin, or lead. Master rod or crankpin bearings in some engines are thin shells of steel, plated with silver on both the inside and the outside surfaces, and with lead tin plated over the silver on the inside surface only. Smaller bearings, such as those used to support various shafts in the accessory section, are called bushings. Porous oil-leak bushings are widely used in this instance. They are impregnated with oil so that the heat of friction brings the oil to the bearing surface during engine operation. Ball bearings. A ball bearing assembly consists of grooved inner and outer races, one or more sets of balls, in bearings designed for disassembly, and a bearing retainer. They are used for shaft bearings and rocker arm bearings in some reciprocating engines. Special deep groove ball bearings are used to transmit propeller thrust and radial loads to the engine nose section of radial engines. Since this type of bearing can accept both radial and thrust loads, it is used in gas turbine engines to support one end of a shaft, radial loads, and to keep the shaft from moving axially, thrust loads. Roller bearings. Roller bearings are made in many types and shapes, but the two types generally used in the aircraft engine are the straight roller and the tapered roller bearings. Straight roller bearings are used where the bearing is subjected to radial loads only. In tapered roller bearings, the inner and outer race bearing surfaces are cone-shaped. Such bearings withstand both radial and thrust loads. Straight roller bearings are used in high-power reciprocating aircraft engines for the crankshaft main bearings. They are also used in gas turbine applications where radial loads are high. Generally, a rotating shaft in a gas turbine engine is supported by a deep groove ball bearing. 1-23. Radial and thrust loads. On one end and a straight roller bearing, radial loads only. On the other end, propeller reduction gearing. The increased brake horsepower delivered by a high horsepower engine results partly from increased crankshaft RPM. It is therefore necessary to provide reduction gears to limit the propeller rotation speed to a value at which efficient operation is obtained. Whenever the speed of the blade tips approaches the speed of sound, the efficiency of the propeller decreases rapidly. Reduction gearing for engines allows the engine to operate at a higher RPM, developing more power, while slowing down the propeller RPM. This prevents the propeller efficiency from decreasing. Since reduction gearing must withstand extremely high stresses, the gears are machined from steel forgings. Many types of reduction gearing systems are in use. The three types most commonly used are spur planetary, bevel planetary, and spur and pinion. Figure 1-34. The spur planetary reduction gearing consists of a large driving gear or sun gear splined, and sometimes shrunk, to the crankshaft, a large stationary gear, called a bell gear, and a set of small spur planetary pinion gears mounted on a carrier ring. The ring is fastened to the propeller shaft, and the planetary gears mesh with both the sun gear and the stationary bell or ring gear. The stationary gear is bolted or splined to the front section housing. When the engine is operating, the sun gear rotates. Because the planetary gears are meshed with this ring, they also must rotate. Since they also mesh with the stationary gear, they walk or roll around it as they rotate. And the ring in which they are mounted rotates the propeller shaft in the same direction as the crankshaft but at a reduced speed. In some engines, the bell gear is mounted on the propeller shaft, and the planetary pinion gear cage is held stationary. The sun gear is splined to the crankshaft and acts as a driving gear. In such an arrangement, the propeller travels at a reduced speed, but in opposite direction to the crankshaft. In the bevel planetary reduction gearing system, the driving gear is machined with beveled external teeth, and is attached to the crankshaft. A set of mating bevel pinion gears is mounted in a cage attached to the end of the propeller shaft. The pinion gears are driven by the drive gear and walk around the stationary gear, which is bolted or splined to the front section housing. The thrust of the bevel pinion gears is absorbed by a thrust ball bearing of special design. The drive and the fixed gears are generally supported by heavy-duty ball bearings. This type of planetary reduction assembly is more compact than the other one described and, therefore, can be used where a smaller propeller gear step down is desired. In the case of gas turbine turboprop engines, more than one stage of reduction gearing is used due to the high output speeds of the engine. Several types of lower-powered engines can use the spur and pinion reduction gear arrangement. Propeller shafts. Propeller shafts may be of three major types: tapered, splined, or flanged. Tapered shafts are identified by taper numbers. Splined and flanged shafts are identified by seam numbers. The propeller shaft of most low-power output engines is forged as part of the crankshaft. It is tapered and a milled slot is provided so that the propeller hub can be keyed to the shaft. The keyway and key index of the propeller are in relation to the No. 1 cylinder top dead center. The end of the shaft is threaded to receive the propeller retaining nut. Tapered propeller shafts are common on older and smaller engines. The propeller shaft of high-output radial engines is generally splined. It is threaded on one end for a propeller hub nut. The thrust bearing, which absorbs propeller thrust, is located around the shaft and transmits the thrust to the nose section housing. The shaft is threaded for attaching the thrust bearing retaining nut. On the portion protruding from the housing, between the two sets of threads, splins are located to receive the splined propeller hub. The shaft is generally machined from a steel alloy forging throughout its length. The propeller shaft may be connected by reduction gearing to the engine crankshaft, but in smaller engines the propeller shaft is simply an extension of the engine crankshaft. To turn the propeller shaft, the engine crankshaft must revolve. Flanged propeller shafts are used on most modern reciprocating and turboprop engines. One end of the shaft is flanged with drilled holes to accept the propeller mounting bolts. The installation may be a short shaft with internal threading to accept the distributor valve to be used with a controllable propeller. The flanged propeller shaft is a very common installation on most propeller-driven aircraft. Reciprocating engine operating principles. The relationships between pressure, volume, and temperature of gases are the basic principles of engine operation. An internal combustion engine is a device for converting heat energy into mechanical energy. Gasoline is vaporized and mixed with air, forced or drawn into a cylinder, compressed by a piston, and then ignited by an electric spark. The conversion of the resultant heat energy into mechanical energy, and then into work is accomplished in the cylinder. Figure 1-35 illustrates the various engine components necessary to accomplish this conversion, and also presents the principal terms used to indicate engine operation. The operating cycle of an internal combustion reciprocating engine includes the series of events required to induct. 1-24. Spur planetary. Bell gear, pinion. Sunk gear, bevel planetary. Spur and pinion. Driven gear, drive gear, crankshaft. Figure 1-34. Reduction gears. Compress, ignite, and burn, causing expansion of the fuel/air charge in the cylinder, and to scavenge or exhaust the byproducts of the combustion process. When the compressed mixture is ignited, the resultant gases of combustion expand very rapidly and force the piston to move away from the cylinder head. This downward motion of the piston, acting on the crankshaft through the connecting rod, is converted to a circular or rotary motion by the crankshaft. A valve in the top or head of the cylinder opens to allow the burned gases to escape, and the momentum of the crankshaft and the propeller forces the piston back up in the cylinder where it is ready for the next event in the cycle. Another valve in the cylinder. 1-25. Spark plug. Combustion chamber, intake valve, exhaust valve. Piston, TDC, stroke, connecting rod, PDC, cylinder flange, top center, crankshaft, bottom center. Figure 1-35. Components and terminology of engine operation. Head then opens to let in a fresh charge of the fuel/air mixture. The valve allowing for the escape of the burning exhaust gases is called the exhaust valve, and the valve which lets in the fresh charge of the fuel/air mixture is called the intake valve. These valves are opened and closed mechanically at the proper times by the valve operating mechanism. The bore of a cylinder is its inside diameter. The stroke is the distance the piston moves from one end of the cylinder to the other, specifically from top dead center, TDC, to bottom dead center, PDC, or vice versa. Figure 1-35. Operating cycles. There are several operating cycles in use. 1. 4-stroke 2, 2-stroke 3, rotary 4. Diesel, 4-stroke cycle. The vast majority of certified aircraft reciprocating engines operate on the 4-stroke cycle, sometimes called the Otto cycle after its originator, a German physicist. The 4-stroke cycle engine has many advantages for use in aircraft. One advantage is that it lends itself readily to high performance through supercharging. In this type of engine, 4 strokes are required to complete the required series of events or operating cycle of each cylinder. Figure 1-36. 2 complete revolutions of the crankshaft, 720 degrees, are required for the 4 strokes. Thus, each cylinder in an engine of this type fires once in every 2 revolutions of the crankshaft. In the following discussion of the 4-stroke cycle engine operation, note that the timing of the ignition and the valve events vary considerably in different engines. Many factors influence the timing of a specific engine, and it is most important that the engine manufacturer's recommendations in this respect be followed in maintenance and overhaul. The timing of the valve and ignition events is always specified in degrees of crankshaft travel. It should be remembered that a certain amount of crankshaft travel is required to open a valve fully. Therefore, The specified timing represents the start of opening rather than the full open position of the valve. An example valve timing chart can be seen in Figure 1-37. Intake stroke B compression stroke. Intake open, valves closed. Exhaust open, valves closed. See power stroke D exhaust stroke. Figure 1-36. 4-stroke cycle. 1-26. 1 complete actual cycle of a 4-stroke cycle reciprocating engine. Valve overlap 75 degrees, both valves open. Ignition. Finish cycle 25 degrees ATC, exhaust valve closed. Exhaust stroke. Compression stroke. Intake stroke. Start cycle 50 degrees BTC, intake valve opens. Intake valve closes 30 degrees ABC. Power stroke. Exhaust valve opens 30 degrees BBC. BTC equals before top center, ATC equals after top center, ABC equals after bottom center, BBC equals before bottom center. Figure 1-37. Valve timing chart. Intake stroke. During the intake stroke, the piston is pulled downward in the cylinder by the rotation of the crankshaft. This reduces the pressure in the cylinder and causes air under atmospheric pressure to flow through the carburetor, which meters the correct amount of fuel. The fuel/air mixture passes through the intake pipes and intake valves into the cylinders. The quantity or weight of the fuel/air charge depends upon the degree of throttle opening. The intake valve is opened considerably before the piston reaches TDC on the exhaust stroke, in order to induce a greater quantity of the fuel/air charge into the cylinder, and thus increase the horsepower. The distance the valve may be opened before TDC, however, is limited by several factors, such as the possibility that hot gases remaining in the cylinder from the previous cycle may flash back into the intake pipe and the induction system. In all high-power aircraft engines, both the intake and the exhaust valves are off the valve seats at TDC at the start of the intake stroke. As mentioned above, the intake valve opens before TDC on the exhaust stroke, valve lead, and the closing of the exhaust valve is delayed considerably after the piston has passed TDC and has started the intake stroke, valve lag. This timing is called valve overlap, and is designed to aid in cooling the cylinder internally by circulating the cool incoming fuel/air mixture, to increase the amount of the fuel/air mixture induced into the cylinder, and to aid in scavenging the byproducts of combustion from the cylinder. The intake valve is timed to close about 50 degrees to 75 degrees past BDC on the compression stroke, depending upon the specific engine, to allow the momentum of the incoming gases to charge the cylinder more completely. Because of the comparatively large volume of the cylinder above the piston, when the piston is near BDC, the slight upward travel of the piston during this time does not have a great effect on the incoming flow of gases. This late timing can be carried too far because the gases may be forced back through the intake valve, and defeat the purpose of the late closing. Compression stroke. After the intake valve is closed, the continued upward travel of the piston compresses the fuel/air mixture to obtain the desired burning and expansion characteristics. The charge is fired by means of an electric spark as the piston approaches TDC. The time of ignition varies from 20 degrees to 35 degrees before TDC, depending upon the requirements of the specific engine to ensure complete combustion of the charge by the time the piston is slightly past the TDC position. Many factors affect ignition timing, and the engine manufacturer has expended considerable time in research and testing to determine the best setting. All engines incorporate devices for adjusting the ignition timing, and it is most important that the ignition system be timed according to the engine manufacturer's recommendations. Power stroke. As the piston moves through the TDC position at the end of the compression stroke and starts down on the power stroke, it is pushed downward by the rapid expansion of the burning gases within the cylinder head with a force that can be greater than 15 tons, 30,000 psi, at maximum power output of the engine. The temperature of these burning gases may be between 3,000 degrees and 4,000 degrees Fahrenheit. As the piston is forced downward during the power stroke by the pressure of the burning gases exerted upon it, the downward movement of the connecting rod is changed to rotary movement by the crankshaft. Then, the rotary movement is transmitted to the propeller shaft to drive the propeller. As the burning gases are expanded, the temperature drops to within safe limits before the exhaust gases flow out through the exhaust port. The timing of the exhaust valve opening is determined by, among other considerations, the desirability of using as much of the expansive force as possible, and of scavenging the cylinder as completely and rapidly as possible. The valve is opened considerably before BDC on the power stroke on some engines at 50 degrees and 75 degrees before BDC, while there is still some pressure in the cylinder. This timing is used so that the pressure can force the gases out of the exhaust port as soon, 1-27. 1 HP equals as possible. This process frees the cylinder of waste heat after the desired expansion has been obtained and avoids overheating the cylinder and the piston. Thorough scavenging is very important, because any exhaust products remaining in the cylinder dilute the incoming fuel/air charge at the start of the next cycle. Exhaust stroke. As the piston travels through BDC at the completion of the power stroke and starts upward on the exhaust stroke, it begins to push the burned exhaust gases out the exhaust port. The speed of the exhaust gases leaving the cylinder creates a low pressure in the cylinder. This low or reduced pressure speeds the flow of the fresh fuel/air charge into the cylinder as the intake valve is beginning to open. The intake valve opening is timed to occur at 8 degrees to 55 degrees before TDC on the exhaust stroke on various engines. 2-stroke cycle. The two-stroke cycle engine has re-emerged, being used in ultralight, light sport, and many experimental aircraft. As the name implies, two-stroke cycle engines require only one upstroke and one downstroke of the piston to complete the required series of events in the cylinder. Thus, the engine completes the operating cycle in one revolution of the crankshaft. The intake and exhaust functions are accomplished during the same stroke. These engines can be either air or water-cooled and generally require a gear reduction housing between the engine and propeller. Rotary cycle. The rotary cycle has a three-sided rotor that turns inside an elliptical housing, completing 3 of the 4 cycles for each revolution. These engines can be single-rotor or multi-rotor, and can be air or water-cooled. They are used mostly with experimental and light aircraft. Vibration characteristics are also very low for this type of engine. Diesel cycle. The diesel cycle depends on high compression pressures to provide for the ignition of the fuel/air charge in the cylinder. As air is drawn in the cylinder, it is compressed by a piston and, at maximum pressure, fuel is sprayed in the cylinder. At this point, the high pressure and temperature in the cylinder causes the fuel to burn, increasing the internal pressure of the cylinder. This drives the piston down, turning or driving the crankshaft. Water and air-cooled engines that can operate on jet fuel, kerosene, use a version of the diesel cycle. There are many types of diesel cycles in use, including 2-stroke and 4-stroke diesels. Reciprocating engine power and efficiencies. All aircraft engines are rated according to their ability to do work and produce power. This section presents an explanation of work and power, and how they are calculated. Also discussed are the various efficiencies that govern the power output of a reciprocating engine. Work. A physicist defines work as force times distance. Work done by a force acting on a body is equal to the magnitude of the force multiplied by the distance through which the force acts. Work W equals force F times distance D. Work is measured by several standards. The most common unit is called foot-pound, foot-pounds. If a 1-pound mass is raised 1 foot, 1 foot-pounds of work has been performed. The greater the mass is and or the greater the distance is, the greater the work performed. Horsepower. The common unit of mechanical power is the horsepower, HP. Late in the 18th century, James Watt, the inventor of the steam engine, found that an English workhorse could work at the rate of 550 foot-pounds per second, or 33,000 foot-pounds per minute, for a reasonable length of time. From his observations came the unit of horsepower, which is the standard unit of mechanical power in the English system of measurement. To calculate the HP rating of an engine, divide the power developed in foot-pounds per minute by 33,000, or the power in foot-pounds per second by 550, foot-pounds per minute 33,000 or foot-pounds per seconds 550. As stated above, work is the product of force and distance, and power is work per unit of time. Consequently, if a 33,000 pounds weight is lifted through a vertical distance of 1 foot in 1 minute, the power expended is 33,000 foot-pounds per minute, or exactly 1 HP. Work is performed not only when a force is applied for lifting. Force may be applied in any direction. If a 100 pounds weight is dragged along the ground, a force is still being applied to perform work, although the direction of the resulting motion is approximately horizontal. The amount of this force would depend upon the roughness of the ground. 1-28. If the weight were attached to a spring scale graduated in pounds, then dragged by pulling on the scale handle, the amount of force required could be measured. Assume that the force required is 90 pounds, and the 100 pounds weight is dragged 660 feet in 2 minutes. The amount of work performed in the 2 minutes is 59,400 foot-pounds, or 29,700 foot-pounds per minute. Since 1 HP is 33,000 foot-pounds per minute, the HP expended in this case is 29,700 divided by 33,000, or 0.9 HP. Piston displacement. When other factors remain equal, the greater the piston displacement, the greater the maximum horsepower an engine is capable of developing. When a piston moves from VDC to TDC, it displaces a specific volume. The volume displaced by the piston is known as piston displacement, and is expressed in cubic inches for most American-made engines and cubic centimeters for others. The piston displacement of one cylinder may be obtained by multiplying the area of the cross-section of the cylinder by the total distance the piston moves in the cylinder in one stroke. For multicylinder engines, this product is multiplied by the number of cylinders to get the total piston displacement of the engine. Since the volume, V, of a geometric cylinder equals the area, A of the base multiplied by the height, H, it is expressed mathematically as V equals A times H. The area of the base is the area of the cross-section of the cylinder. Area of a circle. To find the area of a circle, it is necessary to use a number called pi. This number represents the ratio of the circumference to the diameter of any circle. Pi cannot be stated exactly because it is a never-ending decimal. It is 3.1416 expressed to 4 decimal places, which is accurate enough for most computations. The area of a circle, as in a rectangle or triangle, must be expressed in square units. The distance that is 1/2 the diameter of a circle is known as the radius. The area of any circle is found by squaring the radius, r, and multiplying by pi. The formula is A equals pi r2. The radius of a circle is equal to 1/2 the diameter. R equals D2. Example. Compute the piston displacement of the PO 14-cylinder engine having a cylinder with a 5.5-inch diameter and a 5.5-inch stroke. Formulas required are R equals D2 equals pi R2. V equals A times H. Total V equals V times N. Number of cylinders. Substitute values into these formulas and complete the calculation. R equals D equals 5.5 inches in divided by 2 equals 2.75 in 2. Equals pi R2 equals 3.1416. 2.75 in times 2.75 in equals 3.1416 times 7.5625 square inches in 2 equals 23.7584 in 2. V equals A times H equals 23.7584 in 2 times 5.5 and equals 130.6712 cubic inches in 3. Total V equals V times N equals 130.6712 in 3 times 14. Total V equals 1829.3968 in 3. Rounded off to the next whole number. Total piston displacement equals 1829 cubic inches. Another method of calculating the piston displacement uses the diameter of the piston instead of the radius in the formula for the area of the base. Equals 1/4 pi D2. Substituting A equals 1/4 times 3.1416 times 5.5 in times 5.5 in A equals 0.7854 times 30.25 in 2 equals 23.758 in 2. From this point on, the calculations are identical to the preceding example. Compression ratio. All internal combustion engines must compress the fuel/air mixture to receive a reasonable amount of work from each power stroke. The fuel/air charge in the cylinder can be compared to a coil spring in that the more it is compressed, the more work it is potentially capable of doing. 1-29. The compression ratio of an engine is a comparison of the volume of space in a cylinder when the piston is at the bottom of the stroke to the volume of space when the piston is at the top of the stroke. Figure 1-38. This comparison is expressed as a ratio, hence the term compression ratio. Compression ratio is a controlling factor in the maximum horsepower developed by an engine, but it is limited by present-day fuel grades and the high engine speeds and manifold pressures required for takeoff. For example, if there are 140 cubic inches of space in the cylinder when the piston is at the bottom, and there are 20 cubic inches of space when the piston is at the top of the stroke, the compression ratio would be 140:20. If this ratio is expressed in fraction form, it would be 140/20 or 7:1, usually represented as 7:1. The limitations placed on compression ratios, manifold pressure, and the manifold pressure's effect on compression pressures has a major effect on engine operation. Manifold pressure is the average absolute pressure of the air or fuel/air charge in the intake manifold, and is measured in units of inches of mercury, Hg. Manifold pressure is dependent on engine speed, throttle setting, and the degree supercharging. The operation of the supercharger increases the weight of the charge entering the cylinder. When a true supercharger is used with the aircraft engine, the manifold pressure may be considerably higher than the pressure of the outside atmosphere. The advantage of this condition is that a greater amount of charge is forced into a given cylinder volume, and a greater output of horsepower results. Compression ratio and manifold pressure determine the pressure in the cylinder in that portion of the operating cycle when both valves are closed. The pressure of the charge before compression is determined by manifold pressure, while the pressure at the height of compression, just prior to ignition, is determined by manifold pressure times the compression ratio. For example, if an engine were operating at a manifold pressure of 30 Hg with a compression ratio of 7:1, the pressure at the instant before ignition would be approximately 210 Hg. However, at a manifold pressure of 60 Hg, the pressure would be 420 Hg. Without going into great detail, it has been shown that the compression event magnifies the effect of varying the manifold pressure, and the magnitude of both affects the pressure of the fuel charge just before the instant of ignition. If the pressure at this time becomes too high, pre-ignition or detonation occur and produce overheating. Pre-ignition is clearance volume 1, 2, 3, 4, 5, 6, 7. TDC, total volume, displacement volume, PDC, figure 1-38. Compression ratio, 1-30. When the fuel air charge starts to burn before the spark plug fires, detonation occurs when the fuel air charge is ignited by the spark plug. But instead of burning at a controlled rate, it explodes, causing cylinder temperatures and pressures to spike very quickly. If this condition exists for very long, the engine can be damaged or destroyed. One of the reasons for using engines with high compression ratios is to obtain long-range fuel economy, to convert more heat energy into useful work than is done in engines of low compression ratio. Since more heat of the charge is converted into useful work, less heat is absorbed by the cylinder walls. This factor promotes cooler engine operation, which in turn increases the thermal efficiency. Here again, a compromise is needed between the demand for fuel economy and the demand for maximum horsepower without detonation. Some manufacturers of high compression engines suppress detonation at high manifold pressures by using high octane fuel and limiting maximum manifold pressure. Indicated horsepower. The indicated horsepower produced by an engine is the horsepower calculated from the indicated mean effective pressure, and the other factors which affect the power output of an engine. Indicated horsepower is the power developed in the combustion chambers without reference to friction losses within the engine. This horsepower is calculated as a function of the actual cylinder pressure recorded during engine operation. To facilitate the indicated horsepower calculations, a mechanical indicating device, such as is attached to the engine cylinder, describes the actual pressure existing in the cylinder during the complete operating cycle. This pressure variation can be represented by the kind of graph shown in figure 1-39. Notice that the cylinder pressure rises on the compression stroke, reaches a peak after top center, and decreases as the piston moves down on the power stroke. Since the cylinder pressure varies during the operating cycle, an average pressure, line AB, is computed. This average pressure, if applied steadily during the time of the power stroke, would do the same amount of work as the varying pressure during the same period. This average pressure is known as indicated mean effective pressure, and is included in the indicated horsepower calculation with other engine specifications. If the characteristics and the indicated mean effective pressure of an engine are known, it is possible to calculate the indicated horsepower rating. The indicated horsepower for a 4-stroke cycle engine can be calculated from the following formula, in which the letter symbols in the numerator are arranged to spell the word Planck. To assist in memorizing the formula, indicated horsepower equals Planck 33,000, where P equals indicated mean effective pressure. In psi L equals length of the stroke. In feet or in fractions of a foot, A equals area of the piston head or cross-sectional area of the cylinder. In square inches,